Hello, everybody. This is Dan Adkins, Mini Analytics. It's noon, so we're going to give just another minute to get going here, and then we'll start with our presentation with Josh, and I'll let Josh do introduce himself and then dig right into it. We'll have some of our Data Tech conference chairs fielding questions from YouTube live. For those of you streaming live, you're about 20 seconds behind. We'll get to those towards the end of the session. And if you're wondering what the musical interlude has been while we spooled up and got the links out and learn our way through this new virtual environment we're in, it's Miles Davis, So What? And that actually I thought was appropriate because that's sort of our new motto in data science, at least to me, is so what? You do all this great data science, so what? What are you going to do about it? Anyways, I'm going to bring the volume back down and mute that. And Josh was a presenter at our Data Tech conference in last year and was one of the top rated speakers. And so we historically like to reprise great speakers, and he's one of them. So I'm going to turn it to Josh, and hopefully everything else is working in this virtual environment.
All right, great. Thank you, Dan. Hopefully all the audio is coming through fine for everybody. Yeah, it's great to be back with the Mini Analytics folks. And Dan, thanks for inviting me. I'm really excited to be speaking today about the latest in explainable AI. So we're going to talk about navigating interpretable and predictive models. And I'm hoping today to give everyone who attends really a playbook, how-to, some very in the spirit of Miles Davis's introduction there. So what? You build a great model. What are you going to do about it? How are you going to use it? How are you going to make people trust it? How are you going to help people to know that it's free of bias? There's a lot of really great research coming out of academia right now and industry, and we will dive into that. So let me jump over to my presentation, put it into full screen mode, and then we'll get rocking and rolling. As Dan said, if you have questions along the way, please feel free to put them in the chat, either in the Zoom or on YouTube, and we will do our best to answer them at the end. So I am the Chief Data Scientist with Domino Data Lab by way of introduction. I've been in the industry for about 20 years and have been following the explainable AI space for at least 5 years. It's a very interesting space. I firmly believe, and many of you might be seeing this already, that model ethics, model bias, model misuse, basically everything we need to answer with explainability is going to be a seminal issue of data science over the next decade. Regulatory requirements have been around for a while and they are just getting stronger. And the cry for trust and understanding is strong across all industries, but especially in industries like health and life sciences, financial services. But really I'm seeing a lot of the executives that came out of financial services now getting grabbed up by other industries, particularly for this use case. They know how to explain their models and they know how to handle auditing and regulation of their models. So this is coming for everybody. So we all got to know how to handle it. And by the way, it's a great addition to your resume if you're a practitioner to know how to handle explainability of models. So we are going to define today what happens in step 2, where the miracle occurs in data science. You might have seen this before. This is a superpixel. The rest of the image is grayed out. You're only seeing the pixel, the superpixel here that was important for explaining what this image was categorized as. So I'm not going to give you the answer right now, but take a look at this and think to yourself, what might this be? I'll give you a hint. It's an animal. What type of animal is this? And we'll see what the model thought and what you think here in a minute. First of all, a very important concept that we need to level on before we get into the details of explainability for predictive modeling. And that's the concept of global and local interpretations, or global and local interpretability. When I first started studying the space, this just jumped out to me right away as a very important distinction. And over time, I'm seeing more and more academic papers really call this out and make it clear what their approach helps with, because some approaches help with global, some help with local, and some help with both, but you have to be very careful under which circumstance you are dealing. Let's start with a fictitious example here. Let's say that we are all data scientists working for a professional sports organization. Let's call it the Dallas Cowboys. And let's say that we need to make a predictive model. And we have a choice. We can build one of 3 predictive models. Each model is going to attempt to predict who is going to purchase more than one ticket next year. We want to find those customers so we can advertise to them. Let's look at model number 1 here. Model number 1, we could build a model that will find almost all the people that will buy those multi-game tickets next year. Okay, keep that in mind. Model 2, we could build a model that told you what combination of characteristics in a particular buyer are really important for making this prediction. And number 3, we could tell you exactly why a given individual, let's pick one individual, we can tell you exactly why they will or will not make a multi-game purchase next year. Now, in predictive modeling and in data science, if we wanted to answer each one of those 3 questions, each question would actually be a different model, probably a different algorithm, and most definitely different graphics and supporting documentation that you would put into that model. So let's dive into those a little bit further. The first one is just high accuracy. Let's just figure out where all the yeses are in this stadium, and let's go out and market to them. We don't care about interpretability in this model. We just care about accuracy. Now let's say that we want to figure out a little bit about how the system works. We're going to call this interpretability with global predictive power or global inference. So we might come to a conclusion that, hey, people in cheap seats who purchase far in advance of the game are going to make multi-game purchases next year, for example. And the last one, the third one, is going to be local inference. We have a point prediction, a point interpretation of one individual, and let's try to dissect that probability of why they're going to make a multi-game purchase next year. Again, you might get 3 completely different algorithms depending on which question you're trying to answer. So the first thing I really want to emphasize is understanding the situation that you're in and understanding what you're trying to do with your predictive model, because it's going to make a big difference, and you'll see that unfold as we go through this. You can ask the same question for deep learning. Let's take images, for example. We want to, model 1, we want to classify all the images correctly. Model 2, we want to get a feel for which features of images in general are important for classification. Or number 3, take a particular image. Why was that image classified the way it was? Model 1, high accuracy. Let's just get it all right. Hat, wheel, bag, balloon, dog. Let's go for it. We don't care about interpretability. Number 2, we want to figure out this system. Here you need to build a model, in this case, a deep net, that has global inference built in. You might understand things like, hey, in general, green objects with varying edge contrast are plants. Well, as humans, we know that, but we want the computer and the model to be able to figure that out. That's a global inference that the model is making. And last, and here's that super pixel again that we saw earlier. We want to be able to determine why this particular image was classified as a black bear. And if we look at the image, we're like, hey, wait, that's not a black bear, it's a cat. We can tell. We're humans, we can see the mouse, we can see the blades of grass, and we can tell that's not a black bear. But if you look at the super pixel on the right, you can kind of see why the computer might have gotten it wrong. There's a little black stripe across the neck. Anyway, the super pixel helps you understand why the model predicted the way it did. And that model, in this case, spit that super pixel back out saying, hey, here's why I thought this was a black bear. So then we can go off and understand our model better, maybe make changes. All right, let me tell a little story. This, I think, is going to be very important, again, to setting up what we're going to see in the rest of this presentation. So several years ago, I was asked by a diesel manufacturer to help predict when diesel engines would wear out. I thought, okay, sounds like a great predictive project. Let's dive in. Let's look at the data. Let's start to figure things out. So as usual, when you jump into a project like this, you want to ask lots of questions. As I asked questions, it turned out that the data they had was not from real life wear out of diesel engines. It was a laboratory high stress test condition data. And so at first, that's not going to be great at extrapolating to when a diesel engine is going to wear out. And 2, as I asked more questions, I learned that really they didn't want to predict when diesel engines would fail. They wanted to understand what components of a diesel engine would correlate highly with engine wear out and engine failure. So this turned into a completely interpretable model they didn't want to predict at all. And in this case, I had to put on my statistician hat instead of my data science hat and approach this completely differently. So again, emphasizing you need to know what situation you're in. One more quick story, University of Arizona, I was helping them do some student success modeling, and they definitely wanted to both interpret and predict. They wanted to predict accurately who was going to be at risk of failure so they could intervene and help these students quickly before they got into real trouble with their grades and had a bad experience at the university. But they also wanted to know a little bit about why the students were failing. The key question that I asked in this case was, what are you going to do with the interpretability information? If you know why a student is going to fail or likely to fail, what are you going to do with that? And it turned out they didn't really have too many knobs to turn, too many levers to pull. They had career services and counseling and academic counseling services. So it turned out that they really just wanted to predict, and we didn't have to worry about interpretability too much, which frees you up to try a lot of different algorithmic approaches that can predict very well. But on the side, they did want a little bit of interpretability, so we had to balance that a bit. So it is a balancing game. And that's the moral of this story and the moral of what you're going to see throughout. And keep that in mind as we go through these different scenarios. In my experience, 80% of the time, it's a balancing game. We got to do a little bit of both. 15% of the time, it's just predict and go on with life. And then 5% of the time, if you're not a data scientist, if you're not a statistician, call your statistician friend and say, hey, can you help me with this one? Because this is just purely interpretation, and we need to use some traditional statistical modeling approaches. All right, let's jump in a little bit and see if we can understand what's going on with black box models. I love this cartoon, by the way, that this is probably our future. All right, I'm going to jump through this quickly. This just motivates why we have nonlinear models, why we have black box models, because they predict really well. If things are linear, a linear model does good, we're happy with life. If the system we're trying to analyze is nonlinear, we need something more complicated like a radial basis function support vector machine off on the right. And these other linear methods on the left don't do that well. So let's jump in a little bit into how do we do this interpretability. This is to understand this situation a little bit better. So first of all, I think this is an important concept to keep in the back of your minds. Let's say that there's a theory that says that these real inputs, capital X, cause a real response, capital Y, via a function that understands this system, capital F. And then let's let the lowercase letters be what we observe out in the real world. So lowercase x and y are measurable variables taken from capital X and Y, and little f is the approximate model for the real underlying system of big F. Here's the thing to keep in mind. When we do interpretable modeling, we're trying to find the little f that best explains capital F. That's why we're in a statistical modeling space. When you're in predictive modeling or data science, you're not trying to solve that problem. You're trying to solve a completely different problem. You actually don't care about any capital letters in data science. You only care about the lowercase letters. You only care about observations, about what's happening in the real world. How do we understand the real world? How do we predict the real world? So you only are trying to predict little y. You could care less about capital F. You just want a little f that predicts little y accurately. Of course, it'd be really great if we could find a little f that both predicted little y and also matched big F. But as Hastie, Tibshirani, and Friedman tell us in the classic book, Elements of Statistical Learning, we can't do that. There's no such F. Trade-offs have to be made. All right, let's jump in and look a little bit at what algorithms and approaches and techniques we have for model explainability that are kind of old school. They've been around for a while, but they're still working, they're still good, so we definitely need to know about these. First of all is very simple, just a fully specified linear model. Don't underestimate these things. Sure, they might not predict that well, but in some cases, you're going to want to start with one of these fully specified linear models because it's going to give you really good local and global interpretability. And then you can build from there into more predictive algorithms and see how much more of a predictive power you get as you climb up that ladder. I won't go through this in too much detail because it's probably familiar to all of you, but you find coefficients and you fit them. And then when you get a particular input, like for example, a house in this case with 3,000 square feet and 4 bedrooms, we can fully specify why we predict that house is going to cost $711,000. 200,000 that's due to the baseline. 210 is due to the zooms in my way to the square footage, and 301 is due to the bedrooms. So fully specified, this is local interpretability in this case, but a very, very strong statement. Fully specified linear models also give you very strong statements for global interpretability. You can interpret this coefficient age here. By the way, this data is looking at the amount of oxygen consumed during exercise. And as age increases, the amount of oxygen consumed goes down negative by 0.165 units. So, and by the way, that's also keeping the effect of all other input variables constant. That's a very strong statement that we can make with fully specified linear models for global interpretability. So keep those in mind. Decision trees are great for both predictive and explainability. You can get both local and global from one tree. The tree gives you the global system. You look at one prediction, you can follow its path through the tree for local interpretability. So trees are great, a great compromise. Variable importance graphs are also really popular and have gotten a lot of traction from by a lot of data scientists in their explainability needs. So don't forget about those. Partial dependency plots, something that I don't see used too much in industry, but it should be used more by data scientists. It's more of a statistical technique, but one that I think data scientists should learn how to use and use appropriately. One thing that I would encourage you to do whenever you do partial dependency plots is try to look for distribution spread. If you just look at this plot without the bottom distribution estimate, you're going to think that this data out on the right is just as important as the data on the left, but since most of the data is living on the left, that's where you should focus, and that's going to have more influence on your predictions. But partial dependency plots are great, so don't forget about those. PCA is also a good way to do a little bit of model interpretability. Break down the variability in your variables to a couple of key components, and then interpret those components. All right, so that's just a brief overview of what we have for kind of traditional techniques for model explainability. Let's jump into what is new and exciting. And then we're especially going to focus on some of the deep learning techniques. When I presented in the summer of, I guess it was last summer, at Data Tech, I focused mostly on the tabular data, traditional machine learning. And there have been some really great advancements in regard to interpreting deep nets. So I'm going to dive into a little bit of that today. All right, so first of all, a note on deep nets to help set the stage and help us understand kind of what we're going to be looking at here. On the left of this slide, you have two concepts that we need to understand. One is that sometimes deep net interpretability is put into the frame of reference of pixel influence. And the other kind of side of the coin, or the other side of the house, is concept extraction. There's more than just these two, but these are the two main approaches to interpreting deep nets. Under pixel influence, you have things like saliency maps. Sometimes that'll help you reconstruct an image, which is kind of cool. You have Lime and Anchor. We have something called Deep SHAP, and sometimes you have things called saliency perturbations. Under concept extraction, we have techniques such as TCAV and ACE. We have AI Lens. We have CapsNet, which also does a reconstruction, and we have interpretable CNNs. We'll talk about these in the slides that come. A note on the right, a little caution of warning. The TCAV authors, when they authored their academic paper, went through and found some holes in common pixel-based approaches. First of all, it doesn't give you global interpretability. If you're interpreting the pixel influence of an image, it just applies to that image. It doesn't apply to your collection of images globally and to the model globally. Second, you don't have control over the concepts that these maps pick. Okay, that might be a problem, it might not. Third, sometimes these maps can produce really weird output. For example, I'll just summarize these next few bullet points. If you randomize the final layer of your neural network, the softmax layer, for example, and then you run the pixel influence again, you'll sometimes get the exact same pixel influence. So often what happens is, no matter what the prediction was, there are certain characteristics of your image that tend to be grabbed by the neural network, and it will always spit those out as influential pixels. That's a tendency of some neural nets that some neural nets expose. So you want to just sometimes take pixel influence with a little bit of grain of salt and make sure that it's been done in the right way. So I'm going to focus a lot of what I talk about under concept extraction, because there's some really neat stuff in that's come out through industry. All right, first of all, let's start with SHAP. This one, so up on the right of each screen, you're going to see a little tag. It's going to say ML models and or DNNs. So this is going to tell you whether this approach applies to traditional machine learning, like gradient boosted machines, random forest, decision trees, and also whether it will apply to deep nets. So SHAP applies to both. If you're not using SHAP, one big takeaway of this presentation is start using SHAP. It's a great approach to interpret, to give model interpretability, both globally and locally. The way SHAP works is it works on a permutation basis. So the technical definition of a Shapley value is the average contribution of a feature over all possible permutations of, so they take one row of a data set, one prediction, and look at each column, look at the influence of that column, randomizing everything else in that row. And then they go through the entire data set and run that permutation test over and over and over and over and over again. So it's very computationally expensive. But that's what Shapley values are. They're proven to be the only surefire way of getting good interpretability. Everything else is an approximation to Shapley values. Even SHAP is an approximation to Shapley values. And they have written, the SHAP authors have written some algorithms that will speed this up and will do, will get you results quickly. If they don't have one of these computational approaches built into their platform for the model you're using, then you can't really use SHAP. It's just way too computationally expensive to do it without one of these algorithms that's been built to optimize it. Let me get back on the screen. There we go. Here's an example of some of the output that SHAP will give you. The top one's called a force plot. It's really cool. So this is the Boston housing data at the top. This is a local interpretability. So this particular input, the whole model had a base value of 22.34. I'm not going to get into what the numbers mean. It's not important for right now. For this particular input or row in the data set, we predicted 24.41. What made it higher than usual? Well, LSTAT being at 4.98 pushed it the most. PT ratio being at 15.3 pushed it second. Then there was some other things that didn't show up on the Pareto. There are a few things that pushed it negative too: RM, NOx, age, and so on. A great local interpretability graph right there. And there's something called Deep SHAP, which is based on pixel influence, which can let you see which pixels in the image contributed to its classification. So SHAP's a great option there for local interpretability. And very important here is SHAP is also good for global interpretability. Up in the top left, you have what's called a summary plot. This shows you every SHAP value along the x-axis and every input feature in the data set along the y-axis. So every dot is a row in the data set, and you have the SHAP values for each of those rows. And the colors that you're seeing here are the values. Let's just look at LSTAT here. So high LSTAT is red, low LSTAT is blue, and you can see where the density of the values are at, which is also really important to have, like we saw with partial dependency plots. So high LSTAT values push the prediction lower, give you a lower SHAP value. And this is just a great plot. You can really get a good global feel for the whole system in with one eyeball swipe. It's really great. Down here under variable importance plots, the SHAP authors have done a lot of research on variable importance plots from random forest packages, from XGBoost packages, and they have shown that those can vary quite a bit under different circumstances, and that these SHAP variable importance plots are the most secure and dependable. So if you can use SHAP, meaning if there's an optimizer for your algorithm, I would highly recommend always using the SHAP variable importance plots from here on out, and don't use those random forest and XGBoost variable importance plots anymore. SHAP's going to be much more dependable in what it gives you, and it won't vary based on a couple of different factors. All right, let's jump into Lime. So Lime's interesting. Lime might be the thing you would think to do if you're just thinking, how do I solve interpretability of a black box model for a local prediction? You might think, well, let's just take that local prediction and build another model around it to try to explain the black box model in that vicinity. And that's exactly what Lime does. It builds a sparse linear model that's highly interpretable around the vicinity of a point prediction. And then you can get graphs like this. It says, hey, for this particular feature, Boston housing data, again, LSTAT in the range of 6 to 11 pushes the prediction up by so much. And you can do that type of interpretation for all those. And that image we saw earlier was from Lime. Lime also gives you superpixels for images. All right. Anchor. Anchor is an add-on to Lime, which is pretty interesting. It tries to find the subset of an image be sufficient to predict the right classification. So here we've got a beagle. The anchor for the beagle is what you see next. And then you can put that anchor on any other image, and it's still going to predict beagle with greater than 0.9% probability. So that's a neat way to dissect an image and break it down and find out what anchors that image in a given prediction. I'm going to skip that slide for the sake of time. All right, let's look at ad tree. If you haven't heard of ad tree, it's very interesting, and I think the concept that ad tree is going after is the future of explainable AI, in my opinion. So what ad tree does, and I when I met Dr. Valdez at a meetup in San Francisco, I saw that he was talking about interpretability, so I'm going to go to this. And when he started talking about his approach, I thought, why hasn't anybody done this before? Maybe they have, but this is the first time I've heard of it. His approach was to, instead of building an algorithm from scratch based on predictive power. So you always hear, hey, I've got a brand new algorithm. It's going to beat this benchmark. It's going to beat everybody else on this benchmark. Why not make a new algorithm, a new mathematical approach to predictive modeling, where the goal isn't only to predict, it's also to explain? Why don't we build a model that can both predict and explain at the same time? Because that's really being asked of us in the industry. And that's exactly what ad tree seeks to do. So it takes it basically has one hyperparameter that you can tune for interpretability. That's pretty cool. If you haven't heard of that, that's just super cool. So what they're doing is they have a continuum between classification and regression tree cart and a gradient boosted tree or gradient boosted stump. And ad tree is a knob you can turn to go from one to the other. So at the end, you get one tree, but if you move it a little bit more toward gradient boosting, it uses more and more boosting to build that single tree. And if you turn it more towards cart, it'll give you less and less boosting, and it'll turn it more towards a traditional classification and regression tree. They've shown that results can still get you pretty good accuracy. You're going to lose a little bit of predictive power, but it's highly, highly interpretable. You get things like this. Here's one simple if-then output for the tree, or like this, one tree that gives you predictive power close to a gradient boosted tree. So pretty cool stuff with ad tree. All right, for the sake of time, I'm going to skip InterpretML. It uses general additive models with interactions. It's built by Microsoft, so you can check out that one on your own later. At the end, I'll show you where to get these slides. So I should have said that earlier, so you don't need to worry about copying down everything. Let's review briefly TCAV, testing with concept activation vectors. This is a global explainability method, which is great. It's global explainability is a little bit harder to do typically than local explainability. So it's nice when we have global options for global. And what TCAV does is it says, all right, build your neural net. And by the way, this is just for neural nets, top right. Build your neural net, and let's consider images for a second. You as the human, as the modeler, get to pick what concept you want to test against this neural net. I've got a concept, and I want to test to see if that concept was captured by my net. So I want to check for racial bias. I want to check for economic bias, whatever. Or I just want to check to see if this factor I'm thinking of, blue sky, is important in the prediction of my images. You get to pick, and then so it has a lot of flexibility, which is great, but you also have to do a lot of hand-holding with it as well. And then TCAV will tell you how important that concept was in the prediction. The example they give is zebras, and we want to see if stripes was important to classifying a zebra. So you build a net, you go and grab your own examples of stripes, which is a little bit cumbersome. You feed it through your net, which right now there's no easy way to do that. You have to do that yourself, also a little bit cumbersome. But then in the output, you get, hey, stripes was important in this particular model. All right, well, we learned something about our model, or stripes was not. TCAV provides, can give you output only if the network learned about it. Okay, so I mentioned these already. There's a few drawbacks. It's kind of, you got to do some hand holding with it. It's not a push button solution today, but it's a really great concept. And here's some examples of how this works. So let's say we're trying to build an image classifier for apron, and we want to see if any of our models, we've got a blue model, a green model, and an orange model, are any of our models biased to female, white male, or baby? And it turns out the green model is. So the green model was looking more at at humans, in particular females and babies, to classify an apron than it was the actual apron. The blue and orange models didn't pick up on these concepts. So a really nice way to test for particular concepts that you have in mind. ACE is an add-on to TCAV, and what ACE does, it goes through and extracts those concepts for you, right? It takes away that cumbersome, hey, I'm going to go and get all these pictures of stripes and feed it in. ACE looks at the images and says, all right, let's try to find the concepts that are important and then put it through TCAV. So a nice little add-on to the TCAV work. All right, AI Lens starts to shift the paradigm a little bit. And if you remember back earlier, we had pixel influence and we had concept extractions for deep nets. So we're still on deep nets here in the top right. AI Lens, or if you search for it in academic papers, it's called influence-directed explanations for deep nets. These influence-directed explanations combine both the influence of pixels and concepts as captured by neurons earlier up in your network. So it combines those two concepts to get you pretty good global and local interpretability. So here's an example. You can take, in this case, the model was trying to predict whether these cars were convertibles or not. And you actually don't see any convertibles in this example, but presumably in the study they did, which I grabbed this from, there were cars with convertibles that the model learned from. And on the right, this is a combination, again, of pixel influence and more abstract concepts that were captured by higher level neurons in the net. And you can see that each of these images is looking at the hood, except for this bottom right one. The bottom, I'm sorry, is looking at the top of the car. This bottom right one is looking at the hood. So most of these images are doing the right thing, which we would want when they're trying to classify a convertible, which is look at the top of the car and see if it's convertible or not. So you learn a little bit about your model and a global instance, and you also learn about these individual images. So AI Lens, influence-directed explanations are really great. I would highly recommend you look into that one as well. Unfortunately, there's no package for this one yet, although AI Lens, I believe, is a startup that you can go and look at and see where they're at with their product. Okay, if you remember how AdTree worked for traditional data, this is its counterpart in deep nets. So interpretable, CNNs, super cool stuff coming out of UCLA. So without any hand-holding like we had to do with TCAV, interpretable CNNs will push your net to build in a way that's interpretable. So you're going to sacrifice a little bit of predictive power, but you're going to build your model from its first principles to be able to both predict and explain. Again, I think this concept of building models from first principles that both predict and explain, and if that means going in and changing how the optimization routines work, so be it. I think that's going to be a highly active area of research and highly used in industry in the coming years. So let's show you an image of a little diagram of how this works. You're going to take these, you're going to force layers of your convolutional net to grab onto one part of an image that's repeated over and over and over again. In the case on the right, you see cats. In the interpretable CNN model, it's focusing just on the face every time for this particular concept that it's extracted. Without interpretable CNN on the bottom, you'll see what it's using to classify cats is kind of different. It's like the feet, the whole body, the eyes, the ears, the paws. It's a little bit of everything mixed together, and it's hard for a human to extract the concept out of that lower set of images. The top one, like, hey, it's looking at faces. I know how my model works, great. And that might be really important in some situations, even worth sacrificing a little bit of predictive power. So interpretable CNNs, I think, are a great thing to look into. Right now, they do have a package out in MATLAB. So if you use MATLAB, go grab that off of GitHub and look at interpretable CNNs and give it a go. I'm looking forward to when this comes out in a Python package as well. All right, I'm going to skip CapsNet for the sake of time, but it's a new method that allows some pretty interesting reconstructions. So you make a prediction and then you say, hey, CapsNet, why did you predict this way? And it'll draw you a picture saying, hey, this is what we saw from the data. This is why we thought it was a 5 or a 3 or whatever. All right, so this slide here shows you a few public knowledge about what these different companies are doing. this isn't inside baseball here. This is what I've heard these companies say at conferences that I've attended. So Lloyd's says, and this is just to let you know what people are doing for interpretability out there in the space. Lloyd's is using SHAP and LIME, but they're also sticking to generalized linear models, or GLMMs is generalized linear mixed models, just a broader family of linear models. FICO recently had an XAI challenge. This was a year or two ago. They were doing a bunch of traditional approaches and they weren't using LIME, but they were aware of it. So they were kind of sticking to traditional approaches that we saw at the first part of the presentation. Bloomberg sticking to linear models and avoiding recurrent neural nets for NLP. They kind of wish they could use it, but regulations require them not to or prevent them from doing so. Capital One, again, documented the benefits of deep learning, but not putting it into production due to regulations and potential bias. So as these, the point of this slide is it's really important that we as an industry get good at explainability, because we're leaving a lot of predictive power on the table when we're not using the best tools that are available for concern about explainability and bias. So as we get better at using these models and understand them and more comfortable with them as an industry, and as academia puts out more and better research and industry too, this is just going to solve this problem as we go along. All right, this is a little bit old, 2018 Kaggle survey, but you can see SHAP and LIME are way down here. I'm sure they've climbed since then. But a lot of people, what are people doing? They're just plotting predictive versus actual. They're looking at feature importance, feature correlations, decision trees. So that's what people are doing as of 2018. Again, I need to get to update this slide. Things are moving, but a point here is if you can get good at these techniques I'm showing you, you're going to be ahead of the game as far as your ability to do something that's very important to the industry, which is explain black box models. All right, let's wrap up my slides and then I'll show you some code, little hands-on portion. So I love this quote by Yogi: if you don't know where you're going, you're going to wind up someplace else. So true. So global interpretability with predictive power is really hard to do. That's one of the key takeaways from today. So for deep nets, if you want to get both this combo of global interpretability and predictive power, I'd look at those interpretable CNNs. They're great. AI Lens shows a lot of promise. TCAP and ACE are really good, but they're still a little bit hard to implement. We need some better Python packages for those. It's just very manual right now. So if you're really expert at deep nets, you can go ahead and use TCAP and ACE, and it won't be too hard to use. But if you're not, there's no push button solution right now. For traditional models, not for deep nets, all interpretability tools really do leave a lot to be desired. Even SHAP with global interpretability, it's a good option, but it's not going to really satisfy some non-analytic executive most of the time. So often you have to sacrifice predictive power if you want global interpretability and use an algorithm that lends itself better to interpretability. So common approaches: build a deep net, gradient boosted machine, random forest, and use SHAP. Right? SHAP was that one tool for traditional machine learning for tabular data that did a really good job, a decent job of global interpretability. Otherwise, you can use trees, elastic net, naive Bayes. They have a little bit more interpretability built into them. Add tree, we saw, that's a good option. And then, hey, maybe just use a linear model, at least as a baseline, right? To see how much predictive power you're giving up with a linear model, because you get a whole lot of interpretability with those. Key takeaway is don't rely on global inference with traditional machine learning models like random forest, deep nets, gradient boosted machines. You need something else. All right, I'm going to skip this. This basically just says, hey, ask a lot of questions so you understand where you're at on the spectrum of interpret and predict. And here's my last slide before I jump into the code. So this is just, I put this together. It's, probably shouldn't be considered as gospel, but it's just the way I see the world. Size of the circle is how much it's used in industry. You've got interpretability on X and predictive power on the Y. So linear models do great at interpretability. They're used a lot, but they sacrifice some predictive power typically. Decision trees are a really nice compromise and used a lot. Add tree is pretty much the same interpretability as a decision tree, but it's supposed to get you more predictive power. So play with that, see how it works. And then if you don't really need interpretability, or if you want to use SHAP and LIME after or some of these other deep net methods after you build the model, just go for it. Gradient boosted machines, random forest, deep nets, and then use a tool afterwards. All right, so I am going to escape out of this. And
While he does that, I'll just again add that we're taking questions in the YouTube live stream. We have a couple queued up there already, Josh. When you get to
Great.
that. You may want to address them, but anyone else, please punch them in. Thank you.
Okay, I'll be sure to save some time for that. So I would encourage you to go to this URL right now. This is, you can get the slides here. You can also get the notebook, the Jupyter notebook, and the R code that I'm about to show you. So I'll leave this up for a second while you go to this address. So this is a Domino's trial site. It's kind of a public place where we can post projects, and you can come in and build your own projects and kind of play around with the Domino platform. But I used it to host all of my XAI content. Also, I have the content on Git, but there's some advantages to having it here on Domino too that I'll show you in a second. Okay, leave it for one more second. All right, hopefully that gave you enough time. If not, you can maybe still see it up there in the URL, but it's just tinier. So when you get into this project, this is my XAI project within Domino. I'd encourage you to take a look at the README, which is just a markdown that Domino lets me put in here to a project. And I've got some advice for you on how to get started. What I would encourage you to do at first is to go and look at the files. And maybe, maybe I can put that in the chat too. I wonder if the Zoom chat will take this. Copy that. Let's see if this works. Is there a Zoom chat? There's a Q&A. All right, let's see if I can. I don't know if I'm going to be able to figure this out. I don't want to waste too much time. So, all right, we'll come back to that in a second. So hopefully you got the URL. Jump over to Files on the left, and that's where you can see the presentation, Shap and Lime notebook, and rtimis.r. Those are the three that I'm going to go over right now. All right, going back to overview. If you want to run this yourself, if you want to do what I'm going to do right now, you're going to need to log in. I'm not going to wait around for everybody to log in, so maybe just watch for now. And then when I'm done, you can follow this login and follow these steps where you fork the project, and then you can go ahead and you have privileges to run and spin up environments. I'm going to go to Workspaces. I'm on Jupyter here, and this is going to be Shap and Lime. Let's put Shap, and I'm going to hit launch. This is going to spin up a Docker container behind the scenes with some AWS hardware in this case. The Docker container has been pre-configured to have all of the stuff I need for Shap ready to go. So I'm also going to spin up an RStudio instance. I'm just going to label that Artemis. You don't have to give it a label if you don't want to. And this is going to spin up a Docker environment that has also has Artemis, all its dependencies ready to go. Well, most of them. There's one more install I need to do. This might take a minute to spin up. This is it's a free version, so it doesn't have a lot of power behind it. So be patient with it if it takes a little bit of time to spin up. We're not a SaaS offering. We install on-premise for enterprises, on-prem or in the cloud for enterprises. So this free kind of SaaS offering takes a little bit to spin up sometimes. All right, so this opened up. It's just Jupyter Notebook. The only thing that Domino adds across the top is you can stop and sync with your Git repositories or your Domino project, and you can. Whoops, did I just hit stop? Oh, silly me! I meant to hit cancel. All right, spin it up again. And if you make a mistake, you can come like that. You can come back and spin it up again. So, all right, we're gonna launch. Oops, I think I launched an R1. No, I just had the R label. That's fine. Okay, so we're going to let that start up again, and I accidentally hit stop there. And while that's spinning up, let's see if we've got a question we can answer. How does Shap achieve randomization? Does it take into account the correlation structure of covariates? No, it's a great question. It's just pure permutations. If you are familiar, if you're into statistics and you're familiar with Fisher's exact test, it's kind of an analogy to that. It just does every single possible permutation of its table, and then it can figure out the importance of variables based on that. The other question, how accessible is a library for writing optimizers and other algorithms? I assume you're talking about Shap there. I mean, you can get this, you can go into GitHub and look at the code and put in your own optimizers. I'm sure they would love contributions to it there. If you're referring to a different algorithm, perhaps let me know. All right, I'm going to open up Shap and Lime. And once that opens up, it's just a plain Jupyter notebook. So Domino is just an open data science platform that kind of orchestrates the world of data science, so it's all under one roof. I'm going to hit run all, so it's just plain vanilla Jupyter. This takes a minute or two to run, So while that's running, I'm going to jump over to my RStudio session that I've got up, and I'm going to open up my artemis.r file, and I'm going to just install Artemis here from GitHub. So this is the only part that takes a couple seconds to go. And while that's going, and behind the scenes still SHAP is running. All right, it wants me to enter. I'll just put a blank space. All right, it's installing, and it should be ready in just a couple more seconds. And then I'll get to show you how Artemis works. Pretty simple, but it's also pretty cool. All right, finishing up. All right, it's done. So let's load it. Look at the package version, and we're going to read in the Parkinson's data. We're going to set the status as a factor, as a new variable. We're going to delete the old status, delete the name because we don't want that. And Artemis has a check data function. So there are 195 cases, 23 features, 22 of those are continuous, 1 is categorical. All right, and now here's the add tree call. This gamma parameter, that's your hyperparameter for interpretability. So it's set to 0.8. It's just so fun to have a hyperparameter for interpretability, and you can swing that around and see what you get. You might lose a little bit of predictive power if you swing it to one end, but you gain interpretability. It's super interesting. So I'm going to run that. It's really fast. Here it goes, and off on the right, we get a confusion matrix. You can also plot the add tree. Let me make this a little bit bigger. So here's your single tree built off of gradient boosting principles, but it spits out a single tree for high interpretability. Super cool. Let's go back over here, and we can show you down here on the bottom left, the decision flow, and you can also put estimates on the end of that. And that's all I'll show you now. You can run through the rest of this code once you fork your own project, or just grab that file and bring it over to your own system. But you can do cross-validation and do some hyperparameter optimization of that interpretability factor parameter. So pretty cool stuff. All right, let's jump back over to SHAP and Lime and see how this is progressing. So at the beginning, we're just installing libraries. We show you the versions. And then we're going to use the Boston housing data over here with SHAP and Lime. Again, just looking at the data, explaining the data. Here we get into the models a little bit. So let's start by building an XGBoost model using the XGBoost library. We'll build the same type of model, also an XGBoost, but from the scikit-learn library. We'll build a random forest from scikit-learn, a k-nearest neighbor from scikit-learn, and then here we go, and here's some code that you can start to build the SHAP explainers. Each explainer from SHAP needs its own code. So in Lime, there's one explainer for the whole model. For SHAP, depending on what approach you use, you're going to use a different explainer or optimizer. If that optimizer isn't there, I just say forget about SHAP. It takes way too long to run. So here we've got a tree explainer for XGBoost, a tree explainer for XGBoost from scikit-learn, a tree explainer for the random forest from scikit-learn, and now we're on to the k-nearest neighbor. There is no explainer for k-nearest neighbor, no SHAP explainer. So what SHAP authors encourage you to do is to run it through a k-means where it summarizes all the data and then run it through its standard kernel explainer. And this just takes forever. And the Boston housing data is really small. So if you ran this on any data of any significant size, it's just untenable. So I recommend going to Lime. But that's what took so long for it to run. And now we're on and looking at the rest of the examples here. So I'll just jump down to the output. Here's that force plot. So you have the syntax that you can look in this notebook to recreate that force plot. Lime, on the version that I have here, doesn't work on the XGBoost library. It does work on scikit-learn XGBoost, which we can see down here. So here's the scikit-learn model, SHAP, you get the force plot, and here you get the Lime plot. So let me put these in the same window so you can see how they look together. So SHAP says that LSTAT was the most important in moving the model up in going from 22.61 to 24.51. And these are looking at the same exact prediction, the same local instance. Then PT ratio, then age. If you look down here at Lime, it switches those. Lime says PT ratio was more important than LSTAT. If they disagree, I go with SHAP, because SHAP theoretically, because it's based on permutations, as was asked earlier, is just more complete. It's more thorough in the way it understands how the model's working. But you still want to know how to use Lime, because there will be times when SHAP just doesn't have an explainer, an optimizer, and so it's just untenable and you need to use Lime. And Lime also I think has really nice explanations here. Its graph, because it puts it in a window, or it says greater than or less than, kind of gives you a sense of how PT ratio affects things and how LSTAT affects things. All right, here's the output for random forest. Again, the two influence graphs. And for K nearest neighbor. For K nearest neighbor was the one we had to do K means on first, and then it took forever. So I wouldn't really trust SHAP with that one, because we had to summarize the data first to even make it finish. In that case, I would go with Lime and trust its prediction more. And then here is the code for doing the variable importance plot, which you'll get out of XGBoost or random forest packages. And here's that one of my favorites, probably my favorite SHAP plot is a summary plot. Again, where you get a feel for just how the whole global mechanism is working. And then down at the end, they do have partial dependency plots. And you can steal some of this code if you want. I wrote a little bit of code to keep the partial dependency plot, but then highlight in black the dot that if we are concerned about one local instance, we can see where that lies in the entire graph. So it combines a little bit of global and local interpretability at the same time. All right, so feel free to play with these on your own inside of Domino. Again, going back to the overview, all you have to do is log in, navigate back to this XAI project from me, and then fork it with this little button at the top, and then you can run what I just did and play around with it. And it's based on Docker, so you're not going to mess anything up, and you can kind of go wild and have fun with it. All right, if you feel like the things you're seeing here with the compute environments inside of Domino that are kind of pre-configured would be helpful to you, I wanted to let you know that you can just Google Domino Compute Environment Webinar. So it's Domino Compute Environment Webinar, and it'll take you to a webinar that's coming up that Domino's presenting that will show you a little bit more about those compute environments. All right, so Dan, I'll pause here. Covered most of what I wanted to cover today, and see if there are any more questions that you have for me.
Sure. So there's, I don't know if did you get the one from Rogue Hogue? John, a second question yet? Kim's queuing those up. While you look at that, I wanted to mention, and Kim's going to unmute, she's going to announce the panel that she's got going next week. But we also have 2 panels in the works I want to make people aware of. We're going to time those for after the semester ends. One's going to be the Angry Hiring Manager panel, and we're going to get some opinionated hiring managers just talk about what they're not liking, and in particular about the college students they're seeing these days. And then the second panel is going to be a WTF I wish I learned in school. And that's going to be a handful of our select, I would call them distinguished data scientists that are quite young and have made a name for themselves, but have realized there's some things that they'd like to see that they would have changed if they were able to transport themselves back in time. So let's take a look at those questions. Kim, did you have anything? I don't think she can talk. So,
well,
Josh,
perhaps
it's back to you.
I'll just give some concluding thoughts here. As I said at the beginning, I really feel like explainability is going to be a seminal issue in data science. It's going to be one that all of us need to have on our resume if we're practitioners, and if we're leaders, one that we definitely need to understand how it works and what our options are, at least, so we can direct our practitioners in the right way. So I just encourage you to stay on top of this topic, keep abreast of what's going on in both deep learning and traditional modeling for explainability. Use those notebooks that I shared with you. I'll put up one more time at the end that URL, just in case you didn't have a chance to get to it earlier. Go here, grab those notebooks, download them. You don't have to log into Domino to download those notebooks and that R file and use it in your own work. If you have any questions further about explainability, I'd be happy to chat about it. I love this topic. I've been following it for a while. So reach out to me on LinkedIn, and I'd be happy to connect and to discuss explainability or any other topics that you might have. Hopefully this has been beneficial for you. Hopefully you enjoyed what we covered today.
I think so. Josh, I want to thank you. I brought up the Miles Davis, if you're wondering. It's so what and I'll let that play. Sometimes I question when people have really great reviews in our surveys, and we get sometimes 345 people that will fill out the survey. So we have a pretty good sample. Sometimes I wonder if, did somebody just brought their posse in? But clearly this is really good information, and I appreciate your time. And I just want to let everybody know I'm going to stop the live stream here after Josh gives us in final remarks, and you'll be able to share this video with anybody on YouTube. It seems to take like a few hours before it becomes readily available across everyone. There seems to be this sort of black hole between the time you stop the live stream and it reconstitutes itself as a watchable recorded video. Josh, final thoughts?
No, thanks, Dan, for having me. It's great to be with the Mini Analytics crowd, and look forward to getting back together in person when we're allowed to. Until then, we'll learn about how to do it virtually.
All right, good. Thank you, everybody.